In today's lecture designed to help prep you for standardized exams, I'll review aromaticity and aromatic substitutions. By the end of this lecture, you should be able to do the following: distinguish between aromatic, non-aromatic, and anti-aromatic compounds, know the names of the monosubstituted benzenes, know how to use the 5 electrophilic aromatic substitution reactions from Chapter 16 in total synthesis, distinguish between ortho-para-directing substituents and meta-directing substituents, predict the products formed when substituted benzenes are subjected to electrophilic aromatic substitutions, know how to use the following reactions in total synthesis: Clemmensen and Wolff-Kishner reductions, radical halogenation of benzyl carbons, benzylic oxidation, and diazonium salt formation, and lastly, predict products and mechanisms of nucleophilic aromatic substitution. So what is an aromatic compound? An aromatic compound is a cyclic molecule whose electrons are delocalized around the ring. This makes aromatic compounds very stable. Here are some cool pictures of benzene, the simplest starting molecule for teaching students about aromaticity. Aromaticity is found all over the place in medicine and in nature. Here are a few interesting compounds that contain aromatic components, such as aspirin, trinitrotoluene or TNT, LSD, heroin, and cocaine. Heterocycles, which are compounds that have more than one kind of atom in the ring, can also be aromatic. Some of the most common aromatic nitrocycles include this: quinoline, indole, imidazole, purine, and pyrimidine. Purine and pyrimidine is of course the base names for the DNA and RNA nucleotide bases shown here, which are also aromatic compounds. To be aromatic, a compound must meet the following criteria. 1. It must be cyclic or polycyclic. 2. All the atoms in the ring must be sp2 or sp hybridized. No sp3s. Now, one note I want you to understand is that atoms that have lone pairs, such as oxygen, sulfur, nitrogen, can make themselves sp2 or sp hybridized as necessary to achieve aromaticity. So if you see an oxygen, sulfur, nitrogen in a ring where it would normally look like it would be sp3 hybridized, it will hybridize itself with its lone pairs to make it sp2 if doing so helps the ring achieve aromaticity. The number of pi electrons in the ring must be equal to 4n plus 2. This is called Huckel's rule. Now note, double and triple bonds only count as 2 pi electrons. Carbocations count as 0 pi electrons. Lone pairs count as 2 pi electrons, but only if doing so solves the 4n plus 2 equation. Otherwise, they count as 0. And charges that are negative, also count as 2 pi electrons. Now, compounds that fail to meet 1 or 2 are called non-aromatic. Compounds that meet 1 or 2 but fail to meet 3 are called anti-aromatic. So here are some great lecture problems. Identify each of the following compounds as aromatic, non-aromatic, or anti-aromatic. I will let you do these on your own. And there are several singly substituted benzenes, which are also called monosubstituted benzenes, whose names you really should know for your standardized exams. Here are a few of them. Well, these actually are they: bromobenzene, chlorobenzene, nitrobenzene, ethylbenzene, etc. Toluene and phenol and aniline, man, these are ones I see all the time on standardized exams. Another common one here is anisole. Anisole is one that you frequently see on standardized exams. Now, one thing I should tell you is that standardized exams written in multiple choice format frequently have the names of compounds such as these written in their multiple choice options, but they often don't show the structures of those compounds. Thus, if you don't know the names of these compounds, you may get the answers wrong even if you actually do know the correct answer by structure. Now, here's a detail that may not seem relevant now, but I want to remind you of it so that you don't get confused on the subject in the future. When benzene is considered a substituent in an IUPAC name, we call it phenyl if it's coming directly off the parent chain, as we see in this example. If there's a CH2 between the benzene and the parent chain, then it's called benzyl as a substituent. So thus we can see compounds like benzyl chloride, diphenyl ether, and dibenzyl ether shown here. And now we arrive at this infamous family of reactions that so often give people hepatitis B, figuratively speaking: electrophilic aromatic substitutions. There are 5 classics we teach undergraduate organic students: halogenation, nitration, sulfonation, alkylation, and acylation. Before we get to these, however, I want to remind you that all electrophilic aromatic substitution reactions have mechanisms that look like this. Essentially, there's some step in them in which electrons come out of the ring and grab an electrophile, generating this intermediate. A base then comes, steals a hydrogen, and closes these electrons like a trap door to restore aromaticity. It is essential that you understand this detail for reasons that will become apparent in a few slides. So here's our first reaction, aromatic halogenation. The overall reaction looks like this. We take an aromatic ring, like benzene in this example, and treat it with X2, where X is either chlorine or bromine, and an iron catalyst, and it places a single halogen on the ring. Yay! Now here's the mechanism which I'm not going to talk you through. If you wish, however, you can pause the video and look it over. The one thing I wish to point out, however, is that the step where the benzene's electrons come out to attack our electrophile, or E+, as I outlined in our earlier mechanistic slide, occurs right here. Can you see that? Electrons come out and grab our electrophile. Some base comes in and grabs this hydrogen, restoring aromaticity. You will see in all 5 of our electrophilic aromatic substitution reactions this type of step being repeated. The only difference between them is the identity of E+. Here is our second reaction, nitration of benzene. Here is that mechanism. Once again, you will notice that the step in which electrons come out of the benzene ring to grab our electrophile occurs right here. This then gives us this intermediate, and the proton is removed to restore aromaticity. Here is our third reaction, sulfonation. Here is the mechanism. Once again, there is a step right here where electrons come out of the benzene, and eventually the proton is removed to restore aromaticity. Our next reaction is this one, Friedel-Crafts acylation. One thing I wish to point out is that this group is called an acyl group. Thus, if we treat an aromatic ring like benzene with an acyl or acid chloride, an aluminum trichloride catalyst, it will place an acyl group onto our benzene ring. Here's the mechanism. Once again, you can see, as with our other examples, there is a step in which electrons come out of the benzene ring and generate some kind of intermediate. The proton is removed to restore aromaticity. And here's our final reaction in the series, Friedel-Crafts alkylation. This kind of group, which can be just any boring old hydrocarbon chain, is called an alkyl group. So if we take an aromatic ring like benzene, treat it with an alkyl chloride and aluminum trichloride catalyst, we can effectively place an alkyl chain onto the benzene ring. Here is the mechanism. And once again, I'm sure you're tired of hearing it, but there is a step right here in which electrons come out of the benzene ring, grab the alkyl group, and this intermediate is then deprotonated to restore aromaticity. Now, I promise that I will point out later on why this is so important. Now, as usual, there are always some details that I have to point out. Here's the detail of the moment. Friedel-Crafts alkylations don't produce good yields for alkyl benzenes containing a straight chain group of longer than 2 carbons because the carbocation rearranges. So this example right here, let's pretend we wanted to get this product, a nice straight chain propyl group on our benzene. We treat under these conditions, what we actually end up getting is this as our major product, in which the carbocation intermediate in the mechanism is rearranged to generate a secondary carbocation, which is more stable. Thus, Friedel-Crafts alkylations don't produce good yields for straight chain groups, or straight chain alkyl groups on our benzene. Instead, the better way to do this type of synthesis is to first acylate it. So if I take benzene and I do a Friedel-Crafts acylation, it will give me this as my exclusive product. Once I get this as my product, I can then reduce the carbonyl by treating it with hydrogen gas and palladium carbon, and this is a way that I can get to my straight chain alkylated benzene as my major product in the sequence. And one thing I need to point out here is that this reaction right here, the hydrogenation of this carbonyl, only works when the carbonyl is at the benzyl position. Now, there are some reactions that can replace a carbonyl oxygen with 2 hydrogens anywhere, even if it's not at the benzyl position. These reactions are the Clemmensen and Wolff-Kishner reduction reactions shown here. Thus, if I take any type of carbonyl, it does not have to be in the benzyl position. It could actually be somewhere else on a boring old straight chain. I treat it with zinc HCl or with this compound and base, I can get effective reduction or removal of the oxygen replacement with 2 hydrogen bonds. This is called Wolff-Kishner or Clemmensen reductions, respectively. So in our example on the last slide where we acylated the benzene and reduced the carbonyl to an alkane, we could also have used Clemmensen or Wolff-Kishner conditions if we had wanted. So what if I do an electrophilic aromatic substitution on a ring that already has a substituent on it, as in this example? So where does the NO2 end up? Does it end up ortho, meta, or para relative to the substituent? The answer is it depends on what the substituent is. Substituents that donate electron density into the benzene ring are called ortho-para directors. Substituents that suck electron density out of the benzene are called meta-directors. Our table here shows several withdrawers, which are meta-directors, as well as several donors, which are ortho-para directors. Now, one way to remember which substituents are withdrawers is to remember that, generally speaking, electron withdrawers, which are meta-directors, look like this. There's an atom A that's double bonded to an atom B that's more electronegative than A. Or there's an atom A that's triple bonded to an atom B that is more electronegative than A. Or the last example is nitrogen that has 4 groups around it, giving it a positive charge. So this is an ammonium nitrogen. I, of course, have my own way of remembering that withdrawers make things or direct things to the meta position, and that is to remember that W equals M. I know that sounds kind of idiotic, but if you look at it, the letter W looks like an upside down letter M. So you can remember that W equals M, which means withdrawers are meta directors. Once again, here is our list of examples of meta-directors, and you can see that all of them fit the description that I've given in this box of being electron withdrawers. Now, substituents that are electron donors, generically speaking, look like this. They're either an atom with at least one lone pair of electrons on it, or an alkyl or aryl group. So let's take a look at some of those examples. But before we do, I want to remind you of my own personal way of remembering that donors are ortho-para directors. And that is by remembering DOPE. Donors direct things to the ortho and para positions. DOPE. So here are several examples of ortho-para directors. The halogens have electron or lone pair electrons on them, and they do direct things to be ortho-para to the ortho and para positions respect of the halogen. One thing I should point out is that these type of ortho-para directors are very, very weak, because although they do donate by resonance, they do withdraw by electronegativity. Thus, these are often referred to as deactivating ortho-para directors. The others over here are all very, very solid ortho-para directors. And now we arrive at some examples. Let's take a look at this. I've got a nitro-substituted benzene. I'm doing a sulfonation on it. Where does the SO3 end up? Well, I have to ask myself, this NO2, is it an ortho, or is it a donor, or is it a withdrawer? Now, of course, if I look at it closely, I'll recognize that it is a withdrawer. The nitrogen's double bonded to an oxygen on one side and single bonded to an oxygen on the other. Thus, it's going to put my sulfonic acid group meta relative to the NO2. What about this compound, toluene? I do a sulfonation of it. Where does the sulfonic acid end up? I have to look at this CH3. What is CH3, a donor or a withdrawer? Well, it is an alkyl group, which is a donor. Thus, the sulfonic acid ends up being ortho and para, so I get a mixture of both products. And typically, the para is usually the major product because of the SO3 being sterically less hindered, being para to the methyl as opposed to being ortho. Here are some more examples. I've got a carboxylic acid, nitrating it. Withdrawing group puts the NO2 meta. Here I've got a chlorine. It's a weak ortho-para-director. That is a weak donor. I'm going to do a Friedel-Crafts alkylation. It's going to end up being ortho and para. And another group. Now this looks kind of confusing, doesn't it? What the heck is going on, and how do I analyze this? Well, the way I think about this is I just look at this whole group as being a donor, and this as being the benzene ring that's going to be substituted. Now, of course, I could do the reverse. It doesn't matter because this molecule is totally symmetrical. Thus, I do this Friedel-Crafts acylation. I have to ask myself, what kind of director is this? It is a donor because this oxygen has lone pairs on it. Thus, it's going to end up giving me the ortho-substituted product and the para-substituted product relative to this phenoxy substituent. Let's ask some more questions. What are the products of the following reactions? Similar type of thing. I'm not going to talk you through this and give you the answers. I want you to look at them yourselves and see if you can come up with the answers on your own. I promise you that if you don't, you will get the chance in class. Now here are some standardized exam style questions to which I think you should pay close attention. I want you to tell me the products of the following reactions. This is one that has several substituents. Where does the new substituent end up? Here's one in which I'm doing something that looks kind of like a Friedel-Crafts alkylation, except I've got the alkyl group attached to the benzene ring. And down here are some general concept questions. How do hydroxy groups direct electrophilic aromatic substitutions? And which of the following reagents could be used instead of AlCl3 and Friedel-Crafts acylation? I'll let you see if you can figure this out on your own. So why are ortho-para-directors ortho-para-directors? Well, to begin answering this question, you have to remember that all electrophilic aromatic reactions follow this general mechanism. Once again, I've said this too many times. Electrons come out of the ring, grab an electrophile, giving me this intermediate. Then a base comes and strips a proton, donates electrons into the ring to restore aromaticity. This is crucial for you to understand. This detail will help you grasp the remaining concept and help you understand the answer to this question. Why are ortho-para-directors ortho-para-directors? So here is the answer. Here's a sample ortho-para-director. If we draw resonance structures, you'll see that I can thrust these lone pairs in, giving me a negative charge at the ortho position, thrust those in, giving me a negative charge at the para position, thrust those in, giving me a negative charge at the other ortho position, and thrust those back to return me back to the original structure. If you look at these, you'll see that this ortho-para-director places a negative charge by resonance on the positions ortho and para relative to itself. Thus, these are the juiciest, most reactive positions on the benzene ring, and those are the ones that attack E+ during an electrophilic aromatic substitution reaction. And the bottom line is that because donors donate electron density into the ortho and para positions, these positions are the ones that attack E+ during an electrophilic aromatic substitution reaction, giving a mixture of ortho and para products. Now I'll show you why metadirectors are metadirectors. Remember that metadirectors are withdrawers, that is, they suck electron density out of the ring. To show you this, I've drawn a generic metadirector right here as an example, and I will prove to you that it sucks electron density out of the ring by resonance. I thrust the electrons up onto this oxygen and thrust these out. It gives me a positive charge on the ortho position. Thrust these over, it gives me a positive charge on the para position. Move those down, it gives me a positive charge on this ortho position, and then I can move these back to restore me to the original resonance contributor. You'll notice that this withdrawer then sucks electron density from the positions ortho and para relative to itself. Thus, withdrawers are placing partial positive charges on the ortho and para positions. So the bottom line for metadirectors is this: because withdrawers suck electron density from the ortho and para positions, the only position left with enough electron density to attack the electrophile E+ is the meta position. Does that make sense? I hope so. Now we move on to a new reaction, radical benzylic halogenation. Thus, if I treat an alkylated benzene like this with Br2 or NBS and light, which is abbreviated HNU here, or HV if you don't have the right font, I will place a bromine on the benzylic position. I have to point out, as my song went earlier this semester, that this position that's immediately adjacent to the benzene ring is called the benzylic carbon. In order for this reaction to work, the benzylic carbon has to be bonded to at least one hydrogen. If so, it will place a bromine on that position, replacing one of those hydrogens. If the benzylic carbon is not attached to at least one hydrogen, it will not place a bromine on that carbon. Now, one thing I wish to point out is that this reaction also works analogously with chlorine and HNu. Thus, I could put a chlorine on the benzylic position as well if I had Cl2 instead of Br2. Now, there are two things that I need to point out here. One is I don't want you to get confused with this reaction, or I don't want you to get this reaction confused with the reaction in which I put a bromine on the ring. Remember, if I take Br2 and I use an iron catalyst, FeBr3, it'll put a bromine on a ring. If I just use Br2 or NBS and light, it puts a bromine on the benzylic position. So those are two different reactions that you should contrast and keep straight in your mind. And the second thing I wish to point out once again is that you can substitute a bromine for chlorine by treating it with Cl2 and light. You might ask me, why, Mike, are you reviewing this stupid reaction? Well, as it turns out, once you have a bromine on the benzylic carbon, you can do lots of synthetically useful things with it. As you may recall from Chapter 8, a bromine is a really good leaving group, which means that if you react it with a nucleophile, the nuke can displace the bromine and give you this type of compound right here. This is an SN2 substitution reaction. Now, here are various examples of different substitutions I might do with my benzylic bromine. So I've got my benzyl bromide right here. Foremost, I can react it with hydroxide to do an SN2 and give me a benzyl alcohol. Also, alternatively, I could react the bromide, or the benzyl bromide, with cyanide, do an SN2 to generate phenylacetonitrile. Instead, if I wish, I can react benzyl bromide with ammonia to do a substitution to give me this ammonium salt. This ammonium salt, if I want, can be treated with base to neutralize it, thus forming benzylamine. Now, another cool reaction that we can do if we have a bromine at the benzyl carbon is an elimination reaction. Thus, if I have a chain of, or a carbon chain longer than one carbon, and I treat it with a big bulky E2 base, I can do an elimination, kicking off the leaving group to generate this product, which is called styrene. If I have this product and I treat it with hydrogen gas and palladium, I can also reduce it to generate ethyl benzene. The humorous thing about this slide is that if you were to treat ethyl benzene with NBS and light or Br2 and light, you would actually produce the starting material. Thus, converting this starting material, 1-bromo 1-phenylethane, into ethyl benzene by this sequence would be a stupid waste of time. However, it does illustrate the ability synthetically that you can of being able to do an elimination here on a benzyl substituted bromide. And now I remind you of another old reaction that you shouldn't forget. If we treat an alkylated benzene with KMNO4 water, or same thing, KMNO4 acid, or sodium dichromate, it will convert all of the benzylic carbons to benzoic acid as long as the benzylic carbons are attached to at least one hydrogen. If this benzylic carbon has at least one hydrogen, this reaction will work. If it does not, then this reaction will not work. So once again, oxidations of tertiary carbons, in other words, a carbon that has no hydrogens on it, won't work because it doesn't have any hydrogens on it. Now, there's a subtle difference between the preceding reaction and this one, where we treat a benzylic carbon with MnO2. MnO2 is a milder oxidizing reagent, but it still requires that this carbon have at least one hydrogen on it. In this particular case, I have to also have this carbon be bonded to an oxygen. So this is a benzyl alcohol. MnO2, if I've already got an oxygen here bonded to my carbon, will oxidize this up one effective bond to oxygen, giving me a ketone or an aldehyde. And here are some cool examples. To figure out the products, I only have to ask myself, is there at least one hydrogen on the benzylic carbon? In this case, there is. So what product does it make? Benzoic acid. On this one, I've taken a benzyl alcohol, treated with MnO2. What does it do? Remember, MnO2 is milder. It oxidizes it up to an aldehyde. Here I've got this compound, treating it with sodium dichromate. Is there at least one hydrogen on the benzylic carbon? Yes, there is. So what product does it make? Benzoic acid. Here's this compound. Is there at least one hydrogen on this benzylic carbon? No, there's not. So what product does it make? No reaction. Here's one last crazy one. When we react this product with KMNO2 or KMNO4 and water, what in the world happens? Well, I have to ask myself, are there benzyl carbons that are attached to at least one hydrogen? Yes, there are. There's one here, and there's one here. So what does it do? It turns both of them into benzoic acid. Thus, the product that I get is dibenzoic acid, shown here. With this background laid, we're now prepared to address these cool lecture questions. Which reaction sequence would convert the starting material shown here to the indicated product? What are the products of each of the following reaction sequences? Which I made up, just to torture you. And now to a new subject, the formation and application of diazonium salts. You see, you can convert aniline, shown here, into benzene diazonium chloride, which is called a diazonium salt, by treating it with NaNO2, sodium nitrite. So why in the world do we care? Well, as it turns out, this compound, a diazonium salt, can be converted into tons of different things by doing these types of reactions. Copper bromide replaces the N2 group with a bromine, copper chloride with a chlorine, copper cyanide with a nitrile group, Ki with an iodine. H3R plus converts the diazonium N2 into an OH, making phenol. Now, one thing that I've pointed out probably too many times to you guys is this. This is the only way of being able to make phenol from benzene. You can't go directly from benzene in one step to having an OH on it. You have to form NO2, then convert the NO2 to NH2, and then convert the NH2 to diazonium salt, and then take the diazonium salt and convert it into phenol using acid. Here are some other things we can do with diazonium salt. HBF4 converts it to a fluorine, and H3PO2 replaces it with a hydrogen. This would be, of course, the most useless synthetic route to benzene itself. Nevertheless, it does show you some cool things that you can do with these diazonium salts. So here are some synthesis questions, much like those you will likely encounter on standardized exams that all involve diazonium salts. What are the products of the following reactions? And here is our final topic, which is one I've never taught you before, but you will likely encounter on standardized exams. Nucleophilic aromatic substitution. Foremost, I want to tell you guys that these two reactions are total crap. Do you see this? Imagine a nucleophile coming in here to a benzene ring, carbon, and kicking off a bromine, or a nucleophile coming in here to a vinyl carbon and kicking off a bromide. These reactions are total crap. Why? Because you can't do an SN2 reaction on sp2 hybridized carbon. Too much electron density here. You can't do it on sp hybridized carbon either, only on an sp3 hybridized carbon. So these reactions will not work. Nevertheless, we still see that this reaction occurs. Do you see this? I can take a chlorine and replace it with an OH. That actually does occur. So what in the world is going on here? Is this an SN2 reaction? No way. You cannot do an SN2 reaction on sp2 hybridized carbon. So what is happening? Well, if you have a withdrawing group on your ring, such as this NO2 right here, as it turns out, you can do this kind of reaction, which is called a nucleophilic aromatic substitution. This is different from an electrophilic aromatic substitution because electrons aren't coming out of the ring to attack an E+. Instead, electrons are going into the ring. Let me show you. Here's my nucleophile, hydroxide. It's coming into the ring. Electrons get moved over there, moved on there, and thrust up onto this electron withdrawing group, giving me this intermediate. Do you see that? This is a different mechanism from the electrophilic aromatic substitution reactions where electrons come out of the ring and attack something. In this case, electrons are going into the ring. Now what occurs? The electrons go back into the ring and they kick off the better leaving group, which is the chloride, to give me this product. Now, interestingly enough, this reaction also works for less reactive withdrawing groups, such as this bromine, if you have a super hot nucleophile like NH2-, which is called sodamide. Here's the reaction mechanism. Our NH2-, which is a super hot nucleophile, much more reactive than an OH-, thrusts its electrons in to this hydrogen that's on the carbon adjacent to this bromine. It does what looks like an E2 elimination to kick off the bromide and temporarily forms this intermediate right here. This intermediate is called benzyne. Now, in a mechanism that probably isn't completely accurate, electrons come out of the benzyne, grab the hydrogen off of the resulting ammonia from the previous step, and then these electrons shared between the hydrogen and the nitrogen thrust in to lock this nitrogen-carbon bond in place. That then gives me my net product, which is aniline, in which the NH2 has been substituted, a net reaction replacing this bromine. So here are our final lecture questions, which all involve nucleophilic substitution reactions. I promise that you will very possibly encounter questions like this on standardized exams. First, predict the product of the following transformation and draw the reaction mechanism. And second, which of the following would undergo nucleophilic substitution most quickly? That ends today's presentation on aromaticity and aromatic substitution reactions. I hope it's been as fun for you as it has for me. I am going to go lie down and take a nap.